How would you run 1,000 tasks and not execute more than 25 at a time? I would like to show you 3 ways you can get this done correctly, including highlighting which one is the most effective and why. So we have 1,000 tasks to run. This could be sending 1,000 emails to attendees for an exclusive event. It could even be calculating the closing day balance for an account for a user who wants to get their account history over a period of time. Given 1,000 tasks, we can run just one at a time. If we do that, we could be grossly underutilizing compute capacity. Well, if there's so much capacity, why not just do all 1,000 at a time? Well, again, if you do that, you could be overwhelming the system and depriving other processes of needed compute resources. You could end up being tagged a noisy neighbor, which is technically the neighbor who, when they're around, no one else can be productive because there's so much noise and so much loud music. So what you want to do instead is determine what number of the total tasks you want to run at a time based on available capacity, which is why we are being told to execute only 25 of the 1,000 tasks at a given time. Let's see some solutions in JavaScript. Let's begin with this JavaScript solution that doesn't use any library, which is why it's in the without lib.js file. So we're not using any library here. But I like to work my way backwards from the actual outcome of the code so that we can make sense of the code when we go through it. So we are running 2 out of 5 tasks just to simplify the example. We're not running 1,000 tasks, but you can see the outcome of doing that execution. You can see that the tasks are run in batches. The first batch starts and task 1 and task 2 get started and then they complete. And only after this batch is done do we begin the next batch, and so on and so forth until we get to the last batch that has just one task. So let's take a look at the code. It's really, really simple. We start here, and what we are doing here is mostly creating a bunch of 5 tasks and declaring that only 2 can be run at a time, and then passing those to the execute without library function, which is where the work is actually done. In there, we try to execute all the tasks within a batch, collect the results in this done array, and return it when we are done. So what are we really doing here? If you observe closely, you would see that we're getting a slice. So if we have 1,000 tasks and we need to do only 25, we get a slice of 25. And once we have that batch of this subset of tasks that we need to execute, we execute the tasks here and put the results in the done array and then just return it when we are done. However, one of the issues with this solution is that we are manually trying to determine what the slice is, which is what the subset of tasks will be. And for each iteration, we also need to manage that slice and calculate it correctly, including making sure that we don't go out of the bounds of the overall to-dos, because if we do that, that will lead to an error. This is repetitive and very error prone. I mean, once you've gotten it, it's fine, but it's error prone if someone's going to be maintaining and managing this code. So if there's a solution that allows us to achieve the same results without having to manage the bounds of the slice and array indices and all of that and risk array index out of bounds error, then that solution will be much better than this one. Let's take a look at that. This next solution is very similar to what we already saw, except that it uses a library called n-tuple array, which I made. So let's see how using that library simplifies things. So this is the same code that we saw before, except that this time the execute function uses a library. The library exposes this function called tuples from array. So how does this work? You mostly call it, you give it a list of items you want to iterate over, and you tell it the maximum amount of items it should give you per iteration. So what this means is if we have 1,000 things to do and we say only 25 items should be gotten out of that 1,000 at a time, then this iterable that we get, as we iterate over it, we will only get 25. This significantly simplifies our code such that once we iterate over the iterable, batch will always be the right size of items, no matter what the total size of to-dos were. Given that, we can execute our batch, collect the results, and put them in done. And once there are no more batches to execute, this loop is going to exit and we just return our done. And we are done. So let's see if this works as advertised. So you can see we're running 2 of 5 tasks. They run in a total of 3 batches, and we see the complete results at the end of the day. This is very similar to what we saw when we ran the example without a library. However, if you compare the code for using the library versus the code for not using the library, you can see the difference is really clear. This is a much simpler, concise solution, even though the outcome is the same. Looking at this output, it's very easy to think that our job is done because we can clearly see that we can execute only a subset of the total tasks at a given time. However, our job is not done because there's a very big problem with this solution that is not obvious. Let me show you that in a more visual way. As an illustration, let's imagine that these are the 5 tasks that we need to run, including their durations, which are randomly generated. You can see that so far, this is how we are executing the tasks. They run in batches, and the next batch doesn't get to begin until the previous batch is done. To complete the 5 tasks, it's taking us 3 seconds. However, there seems to be some idle time in the batches when one task is taking much longer than the other. And so the way things are run right now, task 3, 4, and 5 doesn't get to begin even if there's idle time in batch 1. There's idle time in batch 1 because task 1 is completing in a very short amount of time, and that idle time is not being used to even attempt to begin any of the other tasks. And that's where the problem is. The opportunity cost for this is that out of the 3 seconds that we are spending to complete the entire 5 tasks, potentially 2 of those 3 seconds are spent idling away and not doing anything. We can optimize this process by making sure that if there is idle time, we can make use of that time to execute more tasks so that we can shorten the latency and reduce the overall time taking us to complete the 5 tasks. And so that's what this problem is, that it's not easy to spot. Any solution that we come up with next should be able to address this problem of making sure that we are optimizing for idle time if the system has more capacity for that. And if we do that, this is how our solution should be. We should be able to kick off task 1 and task 2, but as long as task 1 is done, we should begin to attempt to do any of the other tasks that are still available so that overall we should be spending less time. Essentially, we should be running the tasks concurrently such that as soon as any of the 2 that is being run at a time finishes, any, not both, not all. As soon as any of the tasks finishes, we should be grabbing the next available task and running that as well. Let's take a slightly deeper look at what concurrency means. Let's look at some modes of execution to see why concurrent mode might be a good one. So let's imagine that there's a pro Scrabble player who has to play 5 other players. There are a number of ways this can pan out. The first scenario is that the pro player can play each of the other players one at a time. And that's the serial execution, which we said initially that will be slow and will take a lot of time. I did some math, and from my estimation, it will take about 55 minutes for that scenario to be completed. Let's imagine for a moment that there are 2 pro players instead, and they play one of the other players each. So this is like doing serial with 2 pro players. This might speed things up a little bit, but it's still not the best because the pro players are playing the other players one at a time. It's still doing the job one at a time, but maybe with just more capacity. So while the serial execution took about 55 minutes, this parallel execution, because there are 2 pro players playing at the same time, will take about half that time, so about 28 minutes. So it's a little bit better, but it's still not the best we can do. This third scenario is where we have one pro player, but he or she is playing the other 5 players at the same time. He or she plays his or her turn and then goes to the next player to play his or her turn and then goes to the next player just like that. So all 5 players are seated and they are ready and they are engaged to play at the same time, but the pro player goes over them to play his or her turn. This is a much better arrangement because all the 5 players are playing at the same time and things get to run much faster. This should take about 10 rounds for the pro player to finish playing all 5 of them, given that the game overall should take a maximum of 10 minutes. And so with this setup, and from my estimation, it should take about 13 minutes for the pro player to finish playing all 5 other Scrabble players. This is a much better way to solve the problem and to play the game because all 5 of the other players are engaged. There's no one sitting idle and waiting, and the pro player gets to play all of them at the same time, except that he's playing his turn at a given time. And so this takes 13 minutes, which is 4 times faster than the serial execution. The final way to get this game done is to have what we call concurrent parallel execution. In this scenario, we have 2 pro players, but they are playing the other 5 at the same time. So just like we did for the concurrent scenario, this time we have 2 pro players playing the game. So this will take, again, half the time that the concurrent scenario took. It's going to take about 7 minutes from my estimation. So you can see how significantly lesser the time is for completing the entire game of playing Scrabble with 5 players as we go from serial to parallel to concurrent and to concurrent parallel. So the top 2 recommendations for this kind of work will be to do concurrent parallel or concurrent. Concurrent parallel is what you would choose if you are running the tasks in a system that has multi-core processing and you have access to that multi-core processing. So in JavaScript, for example, if you're running this in Node.js on the server and you can create new processes or child processes, then all the other ways to get this done, then that makes sense. On the web, if you're using web workers because they have access to low-level multi-threading, which JavaScript doesn't have because JavaScript natively is single-threaded on the browser, then you can do concurrent parallel execution. Let's implement our final solution in code with the concurrent execution mode. All of this to improve the latency of our solution. Our code is laid out just like the other solutions that we've seen. We begin here where we create a bunch of 5 tasks and 2 is to be run at a single time. And we pass that to the execute concurrent function, which is where the work of our solution needs to be built. Let's begin by creating the batches. So we can do that by doing this. So we initialize our batches. We're going to be using the max batch size to do that. So I can create an array that we're going to populate from that batch size. So we can say the length of our array should be the max batch size. And we're going to be mapping the elements that will be created in this array to some form of worker function, which we're going to create soon. Okay, so at the end of this, we should have our batches in which we're going to be running the tasks, and the batches will correlate to the batch size. And all we have to do is just to run the batches. And so our next task is to create the worker function, which will eventually run the tasks that we've captured now in the batches. Let's continue by building out our worker. We start here by getting one of the to-dos that needs to be executed from the collection of to-dos. So we get the first one that's available, and we go into some form of loop. And our condition is to check that this to-do that we want to execute is actually something. It has value. It is not undefined. And within our loop, we want to make sure that we can exit that loop safely. So what I like to do is that as soon as I go into a loop, I create my exit condition. So we do to-do equals to to-dos.shift. So this means that we're getting the first to-do in the list of to-dos. We go into a loop where we're going to execute our code, and we make sure that we keep assigning to-do to the very next one that is available. At the end of the day, when we run out of to-dos, to-do here is going to be undefined, and this loop is going to exit. Now let's continue by actually executing our tasks. So once we have this, all we have to do is to add that result that we've gotten from executing this to do. We just want to add it into the collection of results, which we're calling done. this should be const. And if we run this code, everything should pretty much work like the two other examples that we've seen, except that now when we are running two tasks at a time, we don't have to wait for both of them to completely finish before pulling the next available task. As soon as any one of these two finishes, then we'll be grabbing the next task and running it such that we still have a maximum of two tasks running at a time. Before we run this code to see how it runs, there are two tiny fixes I need to make. So here, we need to change this from const to let because we are reassigning it down here and we can't do that to a const variable. And secondly, we are trying to execute a promise here, but we're not awaiting it. So with those two fixes out of the way, we should be able to run our code now and take a look at the output. You can see that we are running 2 or 5 tasks concurrently at any given time. And if you observe the output, you will see that task 1 and task 2 starts. And as soon as task 2 completes, we start task 3 immediately, right? Task 1 is still running, okay? As soon as task 2 completes, we begin task 3. Task 3 has also completed, interestingly, and we begin task 4 before task 1 completes. So you can see that 2 tasks are running max at the same time, but as soon as any one of them finishes, we pick up the next task. There are a couple of potential improvements to highlight in this code. One would be the fact that we're using Promise.all.settled here. And so why are we doing that? We're doing that because we want to execute the tasks and gather the results from the sync processing, whether they are successful or whether they fail. And Promise.all.settled allows us to do that. It runs the promises and gathers the results of running those promises, whether they succeed or they fail. If we use Promise.all here, then we are going to get a halt or a failure of the task as soon as there's a single failure. And so that potentially can go on here because we're using Promise.all here. Because we're using Promise.all in this place, if the very first promise was a failure, then the entire process could potentially halt. We might want to switch this to all settled instead of Promise.all. Another thing that we can do is here, where we call to-dos.shift, we are potentially mutating this array, and that's not a very good thing to do when you are coding. Mutating means we are changing the to-dos array, and it might be used in other places in our code. So what we want to do ideally is to make a copy of this to-dos array and then mutate that copy. Hopefully this has been a good run. We're looking at how to execute a subset of tasks at the same time, giving a larger pool of tasks. And we saw a number of examples. We started by looking at the without leave example where we wrote vanilla JavaScript without using any external library. It worked, it gave us the correct output, but the code was repetitive and error prone because we had to manually manage array indices and calculate the right bounds and stuff like that. We then took a look at a solution where we used a library, which is the n tuple array library I created. And all these examples and solutions that we've looked at are within that library, which I encourage you to take a look at. And so the with lib solution basically uses that library. We call the tuples from array function in that library. We tell it that we have this 1000 element array. We want to iterate over it, but we want to get only 25 items at a time. And because of that, we no longer have to worry about the right sizing of the batch or the right sizing of the elements coming out of the array at any given point in time. And our code is much more simplified. However, these two solutions did not quite make use of idle time. That is why we saw the concurrency solution, where we were able to make use of any idle time that the system might have, and we were able to cut down on the latency of the solution. And so to wrap up, I wanted to just highlight the library I made. So the second solution that we saw that used a library, used the n tuple array library, which I created. And the reason that this library came to exist was that about 3-4 years ago, I was interviewing for an engineering manager role, and I was asked to live code an application that would mimic people getting into an event hall, but only 2 of them could be attended to at a given point in time. And so that was how this library was born. What it does is you can get a configurable amount of items when iterating over an array. So do check it out. Go to npm.js, check it out, and let me know what you think. And thank you for watching. I hope you learned a thing or two. I'll see you next time.